I'm hearing my own echo. Thank you everyone for coming to one of our webinars this month. This time we have Trevor Kramer, who is presenting his PhD work. This is what the project that he's leading here at Tennessee Tech, at part of the Propulsion, Power, and Thermal Systems Laboratory. This work was funded by RPE, Department of Energy, RPE, through the REACH project. And Trevor has been working on this for about a couple of years, a little bit over 2 years now. Has done a lot of work in modeling and testing. And I'll just go ahead and hand it over to you and present to everyone.
Yeah, thank you for the introduction. Thank you for all the attendees today. I really appreciate your support coming out to listen to us. So today I'll be talking about some of the work we've done, as Dr. Robertson mentioned, for the RPE REACH program, and the simulation analysis of a solid oxide fuel cell combustor hybrid power generation cycle for the focus on commercial electric aviation applications. So get into a little bit of the motivation and background. As the aviation industry is kind of moving towards some like next generation of aircraft, they'd like to go to a more sustainable operation, as well as more environmentally friendly, lower environmental impacts, and lower these greenhouse gas emissions while still being able to maintain our current standards of commercial passenger air travel. So this involves, probably having a higher efficiency aircraft, power generation method, and some of these next generation concepts. An example can be seen here in the NASA's NX-3 blended wing concept that has distributed electric propulsion. And, whether it be this concept or maybe a narrow body electric aircraft, a lot of these concepts require a very large amount of electrical power generation. So maybe around 29 megawatts of peak power generation. Put that in perspective, in Tennessee, I think the average daily use of energy is around 38 kilowatt hours, which we are one of the highest energy consuming states in the US, and that's per household. So this power generation during takeoff, if you assume like a 30-minute takeoff, that's around like 12,000 homes for a 30-minute takeoff. So this one aircraft would need to power 12,000 homes, which is pretty significant. So our solution to this, or one of the possible solutions to this, is our SOFC gas turbine hybrid cycle, which I'll begin talking about now. So kind of looking at a conventional cycle, you can see the diagram here, conventional SOFC hybrid cycle, where you have kind of removed the combustor in your typical Brayton cycle and you replaced it with this fuel cell. In our case, SOFC, it could be a different type of fuel cell. And I just saw a question in the chat. Yeah, I'll be sure to answer questions at the end of the presentation, but thank you for the participation. Where you use the fuel cell to extract more of the chemical energy stored in the fuel, so you get that higher chemical to electrical conversion efficiency. And this system shown here, is one of its pros is that it is designed to really have extremely high efficiency, utilizing turbine exhaust recuperators as the main method of thermal management of the SOFC stack, as well as utilizing the SOFC waste heat to extract more of that electrical power from that from that heated flow. But a system like this is not really suitable for the highly dynamic environment that an aircraft would experience, mainly because this cathode heat exchanger has a lot of thermal mass and just added mass to the system that does not allow for quick changes in the SOFC thermal control. This recuperator also requires high temperature valves to control how much air is being sent to that heat exchanger, which adds to the complexity of the thermal management system, and also adds back pressure to the turbine, which limits how much you can fully expand that pressurized flow. So our system shown here, which I'll get into a little bit deeper later, is an SOFC Combustor system, so a little bit different than that conventional hybrid. So shown here is kind of the full schematic of what we're conceptualizing for this aircraft with a combined power and thermal management system. So if any of you were here in some of our previous webinars, we had a student, Will Meacham, present on the thermal management system shown in the dotted blue line, which usually utilizes cryo LNG to cool a lot of the electrical components in the system, such as the generator and the turbogenerator, the motors for the distributed electric propulsion, as well as some of the other electrical components. But what we're really focused on in this presentation is the ESPG portion, so the portion shown in red. And what we're being fed is that vaporized LNG, so like natural gas, into our fuel cell and a post-combustor. So kind of looking deeper at this ESPG concept, this SOFC combustor concept, you can see how it differs from the conventional system presented previously, where our main source of stack thermal management is this SOFC combustor. Shown on the right, you get a little cartoon drawing of how this may look, where the fuel is sent down the tube, perpendicular, or not perpendicular, parallel, but in the opposite direction as the incoming cathode flow. This fuel exits the tube, meets the incoming compressed air, or incoming compressed air sent from the compressor, and combusts. And this combustion process is really how we thermally manage this stack, by controlling the combustion temperature and airflow down, which then affects this pre-combustor exit, the cathode flow, helping us to be able to handle this dynamic environment of the aircraft, which ranges from around 30 degrees C at sea level to around negative 54 degrees C, 35,000 feet, going from 1 bar to a quarter bar up at altitude, which I'll get into the simulation results later, but we are able to handle these large perturbations. This SOFC combustor also eliminates, this cathode heat exchanger, which is one of the reasons for the quick response time, and what also gets rid of mass, as well as any of the high temperature valves, and just replaces them with a fuel control valve. Another component of the system that adds reliability and some redundancy is the post-combustor of the SOFC exhaust. So during portions of the flight where you have a very high power demand or require a very high specific power density, such as takeoff or an aborted landing, you'd like to be able to ramp up the power of your turbine, and you can do this with the post-combustor, increasing the turbine inlet temp, allowing for more power to be drawn off that gas turbine shaft. This also adds a little bit to the reliability, and if there is a failure of the SOFC at any portion of the flight, you're able to kind of sacrifice the system thermal efficiency in order to generate the vehicle's power demand with the post-combustor. Some of the cons of this system is that it's never been fully demonstrated at such a large scale that's going to be required for this electric aircraft, as well as the SOFC durability and cycling itself needs to be proven out for these higher performing tubular fuel cells. So what we've done here is created a dynamic system model of the ESPG shown on the previous slide, and run it through an example flight profile shown here, where there's around a 15-20 minute warm up, 40-minute standby, 30-minute takeoff, which where you have that 29 megawatts of required electrical power under peak conditions, around a 5-hour cruise once you're at altitude, with around 10 megawatts of required power, and then initial descent. In this simulation, we are including a emergency takeoff, or a missed approach, they call it, on landing, and then final descent and landing. We've done some with our work with ARPA-E. They've done some work with Boeing to kind of come up with a mass budget for the system. So you see this ESPG mass has to be less than around 26,000 kilograms, including the fuel of choice, as well as just to reiterate this large ambient condition range. So before talking about some of the dynamic results, an important component of this system is the SOFC itself. And its performance is has a large effect on the overall swap of the system, which again we'll be getting into next month. talking about this SOFC Combustor swap. But looking at the SOFC performance here, we've chosen a performance that is similar to some of our targets in our REACH program. So a peak performance around 0.91 watts per centimeter squared. And our SOFC model itself is a quasi 2D transient model. You can see a kind of simplified cartoon in the bottom showing the discretized SOFC tube, solving the energy equation and species conservation equation at each node. We do consider internal steam reformation and the water gas shift kinetics as well. It's because we are utilizing methane as our primary fuel on that anode nickel catalyst. We are assuming that in this SOFC stack, which is around 100,000 tubes, each tube is operating identically, and this just helps to speed up the simulation and kind of capture an average SOFC performance of the entire stack. To capture some of the performance change with pressure increase, we're utilizing fixed law of diffusion through the SOFC electrodes, which I'll get into here, comparing it to the dusty gas model, which is widely accepted to capture these gas mole fractions through the electrode. It's a widely accepted method, but it's not really computationally cheap when you're trying to simulate an entire system. But it is able to capture, multi-component gas flow with varying species. Whereas, we've taken the approach of utilizing fixed law of diffusion, which is easily integrated and just provides a linear relationship. And then a method developed by Fairbanks and Wilkie to come up with a kind of modified diffusion coefficient, shown here, the equation shown here on the slide. And then combining that, assuming it occurs in parallel with Knudsen diffusion, we can get a kind of an effective diffusion coefficient that when comparing the results to the dusty gas model, we see pretty good agreement and definitely acceptable for a full system model. The two charts shown here, at 1 bar and 20 bar, and the Wilkie Fairbanks model shown in solid lines compared to the dusty gas model shown in the dotted lines. One drawback of the Fairbanks model is that you need a specified molar flux of the gas species across the electrode. So in the case of the oxygen, steam, and hydrogen, you have the easily specified molar flux, provided by Faraday's law. But if you try to specify a flux for nitrogen, you need to come up with another method, or just assume it's zero. So you won't be able to capture those gas species through the electrode. But the ones you care about are really just the oxygen, steam, and hydrogen, because those the partial pressures and gas mole fractions play a large role in the SOFC electrochemical over potentials. So kind of pivoting back to the simulation, we can kind of look at our system startup control strategy, which I'll show some warm-up plots of the SOFC on the next slide, where each of these little rectangles kind of represent a simple PI controller. So when we ramp up the gas turbine RPM to a specified set point, that then provides kind of our post-combustor fuel controller with a turbine inlet temp set point, so in a cascading function. And then that fuel flow is then what's sent to the post-combustor, and increasing that TIT increases the gas turbine RPM at a constant load. The cathode inlet temp is also controlled as well, which is that pre-combustion temperature, which is a main way of thermally managing the stack. This pre-combustion is only ignited once the TG is up to full RPM in this warm-up study. And then that cathode inlet temp set point is then used to specify that pre-combustor fuel flow. The load and the SOFC current load and the turbogenerator load are both ramped up to a small value once the SOFC is up to operational temps. So here you can kind of see a nominal warm-up on the left and then a rapid warm-up on the right. On the left, it follows the control strategy displayed on the previous slide. You can see the ramping up section. Mouse here, the ramping up section. of the gas turbine. Then we have pre-combustor ignition, all the way to SOFC operating temps, or warm up to SOFC operating temps, and we enter a hot standby, where pretty good temperature distributions across the cell, especially at those higher temperatures where your thermal stresses will be even higher, around 8 to 9 degrees Celsius. These simulations are assuming perfect fuel valves, so there's no delay for fuel valves currently. This would probably provide possibly a 2 to 10 second delay in that fuel flow, which this system could definitely handle, and that's definitely one of the things we're looking to add in the future is those valve dynamics of the fuel flow. Looking at the rapid warm up, this one is not maybe physically possible. It really depends on how fast this turbo generator can be ramped up to full speed. Really based on that shaft inertia. But thermodynamically, this can work to provide a very quick warm up of the SOFC. But as we're seeing here, you'll see very large temperature gradients across SOFC. Close to 300 degrees Celsius, which definitely would not work for any planar stack. But in our case, when we're utilizing anode supported tubular SOFCs, could work, but would probably put too much stress on the cell and really decrease its durability over time. So kind of looking at the flight control strategy now that we've passed warm up, we almost have like kind of a 4-step cascade controller that is ultimately controlling the vehicle load demand and also the SOFC thermal management. So we have a max temp allowable for the SOFC. So in our case, it's probably around 750 to 800 degrees Celsius. And then that is compared to the actual maximum temperature, looking at the actual maximum temperature to specify the gas turbine RPM. And this gas turbine RPM is really a large function of how much air is flowing through the SOFC, which is another way that we can thermally manage a stack is by adjusting this RPM. Based on that set point, we control how much load is being drawn from the turbo generator. Now this turbo generator load is it does have bounds, within our controller of max and mins, but it is kind of just an arbitrary value that we take what we can get, really based on our scheduled turbine inlet temp set points. So the power demand that is not provided by the turbo generator is then made up by the SOFC, which is then fed into another cascade controller, setting the voltage based off how much power we need to ensure that the voltage does not go to a dangerously low level, and then that voltage set point goes into how much current load we are drawing from the SOFC. Where in each of these controllers, we can also specify how much these values are ramped, and how aggressive they are to also maintain the safety of the SOFC. The cathode inlet temperature and the turbine inlet temperature are controlled pretty simply, but they are scheduled throughout flight based on power demand. And they're just based on that temperature set point, maintaining a specified fuel flow. So now we can look at some of the load following characteristics of the SOFC, where the black line is the vehicle power demand. And even though we have these aggressive step demands, and during this takeoff, we're going from sea level to around 35,000 feet, so highly dynamic. And you can really see the load changes in the SOFC and the TG. We're able to meet these demands in about 20 seconds. Hopefully you guys can't hear that construction in the background, but if you can, they're working hard. So yeah, so these aggressive power demands are met relatively quickly, around 20 seconds. And even ramping even harder could really harm this SOFC, but that was one of the things we were looking to test out experimentally. If you're curious, the power split, during takeoff peak conditions around 23, 77%, respectively for SOFC and the turbo generator, and this pretty much mirror flips during cruise. During cruise, we are not operating the post combustor unless in a reality we would need to compensate for a damaged SOFC. But in this ideal simulation, the post combustor does not operate, which helps us raise our system efficiency. So one of the main things that we're trying to promote with with this system is that thermal management of the SOFC. So here you can really see on the top surface that SOFC temperature distribution along the cell during takeoff, where the actual like average temperature is fluctuating quite a bit, but the temperature difference across the cell is staying relatively low to what we've seen in some of our experimental testing, as well as some of the work we've done with special power sources, a company out of Alliance, Ohio, some of the temperature difference that they've seen in their system operations for remote power generation. And then during cruise, we're down to about a 22 22 degrees Celsius delta T across the tube. And yeah, just looking at the takeoff and missed approach, we are able to kind of keep this SOFC temperature distribution, pretty small, even though with these, large ambient air changes, as well as, operating pressure changes, mass flow changes as the density changes, as well as load changes. Now we can kind of look at how the gas turbine is behaving during this flight. So what we're doing to capture some of the behavior of the gas turbine is utilizing normalized performance maps. So these are normalized based on user-defined like design mass flow, design speed, and design pressure ratio. So this allows you to kind of resize the turbine to meet whatever system you're trying to simulate. So here you can see an example of the normalized compressor map, as well as the operating line for this flight. We capture the shaft dynamics by specifying a shaft inertia, as well as considering all the different loads on the shaft, including friction loss, as well as the loads of the compressor, the turbine generator, and maybe some accessories as well. So we maintain a relatively high surge margin during the majority of the flight, around 30% or 30. But during takeoff and the missed approach portions of the flight, you see a drop in this surge margin. And this is as the during both of these, highly demanding portion of the flight, the turbine inlet temperature increases dramatically, going from the waste heat of the SOFC temperature around 750 to 800 degrees C, up to around 1400 degrees C, depending on some of the system specifics. And this really drops the density of the flow. So to make up for the mass flow that needs to come through the system provided by the compressor, the turbine has to increase its pressure ratio, which then increases the overall density of that high temperature flow to make up for that mass flow distance that needs to come out the turbine, which then increases the pressure ratio, which is why you see us going down, or our surge margin going down during these highly demanding portions of the flight. But during cruise, we're just operating off the waste heat of the SOFC. So this is not as much of a concern. Still high temperature flow, but the density is not as low during takeoff. So looking at the real-time lower heating value thermal efficiency of the SOFC, you see during cruise we achieve around 62.5% cruise efficiency. And this efficiency is really a large function of the size of your SOFC stack. So if you want to sacrifice some, like I said before, some of your specific power density, you can get a much more efficient system, all the way up to around 70% efficient if you add a lot of tubes. But the size of your SOFC and the performance of your SOFC really affect this swap. The swap considerations of this system, which another preview is that's what's going to be talked about next month by one of our other students, Jeff Webster. So I guess to do a little transition to some of our other work for this project, you can see here our pressurized test rig to test these tubular SOFCs under similar aircraft conditions, which we've used to get data like this. So here you can see 3 different cells we've tested, both in the top row in hydrogen and the bottom row methane. going from 1 to 4 bar A, so 4xing the pressure, and kind of measuring the performance increase that you get. One note to make is that this is not like the performance increase we're seeing does not really line up with what the SOFC model was used in this simulation. But what our plans to do is, use this experimental data as well as probably tuning, some of those diffusion coefficients as well as, some of the SOFC design parameters in the simulation to really fit the same performance increases that we're seeing during testing. But during testing, we are seeing kind of a logarithmic behavior and performance increase. So you'll reach kind of a plateau is what we've seen with performance increase, but it can be as high as, if you're in pure hydrogen, around 34 to 35% increase in performance just from 1 to 4 bar A. But what we see more regularly is around the 12 to 17% performance increase. I'm running a little low on time here, so I'll kind of speed through these last couple slides. But another thing that we're really looking forward to is building and demonstrating a 1 kilowatt SOFC combustor. So you can see kind of a preliminary schematic here, as well as that cartoon of the SOFC combustor. And what this will allow us to do is demonstrate a really large component of the full system, at the real scale. So we'll be able to tune our thermal controls, as well as, really see how this thing operates, and if we are able to thermally manage the SOFC tubes during operations. And in our test stand, we can, mimic the conditions, of the incoming ambient air, as well as the pressurized conditions that this stack might see during flight. But one of the key components, which actually I forgot to mention about the full system, is we are considering some anode recirculation. And this recirculation allows for the use of pure methane as your fuel inlet, because during the electrochemical reactions, you get some steam produced. And this steam will help you break down, that methane and the reformation and water gas shift reactions. So we've done some modeling of this anode ejector pump, which is our solution to solve this recirculation. Because you always have to make sure the pressure is balanced, which I can get into kind of the theory of how this operates. But what we've done is kind of taken some analytical models developed by some other in literature, as well as some CFD models, compared those results, and used those to be able to design an injector and eventually test one out. So we are going to be eventually, testing one of these ejectors in a cold setup to be able to function it with this 1 kilowatt SOFC stack, and will help us to further that demonstration. So just a kind of summary of what I talked about today. The simulated SOFC combustor gas turbine looks like it can be a possible solution for this large electrical power demand of a 737 class electric aircraft, as well as the SOFC combustor itself looks like it's able to really thermally control the SOFC stack to maintain a acceptable delta T across the cell. We achieve, pretty high or a 62.5 thermal efficiency, as well as we'll get into power densities next month. And a couple of things we're planning to demonstrate in the future is the SOFC testing, as well as the 1 kilowatt testing. So I'm running out of time here, but I'll go ahead and open up for questions, and thank you guys for attending this talk. I did see some questions in the chat. If no one has any questions online. Do you guys have it?
Trevor, this is Mark Turner from NASA. Glenn, good talk. I'm going to step back a little bit and ask a question about how, if you're on the runway and this is used for a 737 class airplane, you need to be off the ground and almost at top of climb by 18 minutes. So how do you foresee, I know the time lag for this is quick for fuel cells, but for aircraft performance, just wondering, would there be a battery system that maybe you charge up during this time that you're going up and then use that to power? And then how much battery power do you need, or battery capacity to, because you should be off the ground in a couple minutes. I mean, within a minute is the issue I see.
Yeah, yeah. I mean, in the simulation, we are meeting those load demands in around 20 seconds. But that's a great point you bring up, is using a battery to kind of handle the transients where the SOFC is not able to meet those really big step changes in power demand. And we've done some analysis just by, taking how much power, we're not generating, like the error in the power demand based on how much we're actually generating. And doing that, you see that depending on the SOFC size and, your controls, it'd be like, it's like 700 to 800 kilowatt hours, worst case scenario, batteries. So I mean, that equates to around, 2 to 4 Tesla batteries, just to kind of put that in easy.
Okay, so not
understandable.
huge. No, I mean,
Yes,
not,
so not that big. And if we can handle these, if you can handle the slight delay, then you wouldn't even need them. But in reality, these systems would likely have a battery.
okay, thank you.
I got a question in-house. Were you referring to the warm-up time, or were you referring to like the actual takeoff, like that large step demand?
I just saw 18 minutes and I mean, if you're taking that
Okay.
time and you need that full time, right?
Yeah.
To get
I
to
think
that.
I understand your question now.
And
yeah, so
you
that
don't have
18-minute
anything to do
warm-up.
with all that power you're generating in that warm-up period either.
Yeah, so we are not generating sufficient power in the warm-up, or like the takeoff power in the warm-up. We're like, for this flight, we are assuming that the SOFC has warmed up and is in standby during takeoff, which, would likely, in reality, it might not even have to warm up except maybe once or twice a day, probably just once when the aircraft is started. And then it could just kind of stay in idle and keep warm as it is flying to different locations.
But you need to do something with all that power you generate when it's idling or when it's warming up, right? And that's not necessarily easy to do.
Yeah, that is a good point. At least in this simulation, like the turbogenerator load is only around 100 kilowatts during warm up, which I don't have a number for what, the auxiliary power of an aircraft may need, or maybe you hook up to some of the ground systems as well. And the SOFC is loaded to a pretty low current, but as you're saying, when you add up the 100,000 tubes, it can get substantial. So yeah, that is a good point. During warm up, the SOFC is loaded slightly to help maintain that even temperature distribution. But that's a good point to where the load might go. My first guess would maybe be just auxiliary power in the aircraft, or maybe other ground systems have easy connect to that.
So Mark, maybe I can just jump in, because this is the what I think about a lot, is about the warm-up time and the startup time. And I think Trevor mentioned that a little bit, is that this 18 minutes would be as a cold start. So that might be something you need to do in the middle of the day, or the beginning of your day. But then after that, there should be a sufficient amount of heat within the ceramics, so that as long as your insulation is good, now that's a big if, of course, that you should just be able to maintain your temperature and just be able to have that instant power availability available. So that did go into one of the questions I put in the chat, was like, have you simulated the fuel consumption to be able to maintain the temperature if you're in an idle situation, which so you have that instant power availability. And then I would suspect that if you do that simulation, you'll find that because if you assuming a very good insulation, you would actually have very, very limited fuel consumption to maintain that temperature. So I assume you haven't done that calculation yet.
So I mean, it is included in our full system. It's not shown here, and I wish I could pull a number off the top of my head for that flow rate. I can reach out to you after the fact.
Okay.
And send you that fuel consumption during idle. So that is something we've considered, but not really. I guess what we've assumed is the tank is going to be like kind of topped off on the ground as you're going, or as you're, I guess, waiting for passengers to to get aboard. But yeah, I will make sure I'll make a note of that to send you that number.
Because I can remember that. Oh, I'm sorry. Just to say that there was one of the big things about Southwest Airlines, about their model, about having that airplanes are supposed to land and then take off within like 10, 15 minutes. And so if you're put in that type of scenario, I would imagine you don't have a cool down issue to worry about. You just have kind of instant power when you need it. So over.
Yeah, I have a challenging question to throw at you that's kind of off the wall, but I do like your modeling is really very good. It looks quite comprehensive, but I keep being reminded every time I see this flight profile that you're using, that you're modeling. I keep remembering my days back at General Atomics when we were developing the electromagnetic aircraft launcher. And if you've been reading about that on the Gerald Ford class carriers, they're now going to become the standard. And it just keeps looking to me like it would be a practical thing if airports would start looking at an electromagnetic aircraft launcher compatible to the airplanes that are taking off, because so much of the power and fuel is taxed during that time. That once you then do your climb, the amount that you save is enormous. But I wonder, is it just, as an off-the-wall question, could you actually dream up a modeling of having such a device? You got a mass, and you've got an acceleration that you need to go through, and that's given, and you got a terminal velocity you got to go through, and those are all just dynamic calculations. And then if you assume that the power that it takes to do that is all on the ground and not in your airplane, that subtracts that from your model. Just a wild guess. Could you actually model such a phenomenon and such a system? It looks like you could.
I could try. Yeah.
What does Rory think of that?
What does Rory think of that? Or maybe he could step in. I don't know. Much of us have a lot of experience with the electromagnetism.
I think it would be, well, like I say, I was immersed in it for years, and so it just comes to mind. And every time I read an update on what's happening at General Atomics and an update from what the Navy is doing, I keep being reminded, my goodness, here's this thing that takes planes up to 130 nautical miles per hour in 300 feet, and I think, well, wait a minute, are we that far off here if we make it a little longer and not really have, 2 Gs of acceleration to the people inside? It just looks practical. I know that some conversations when Boeing was on the phone, somebody back there is thinking about it. Now, whether any action is going to be taken, I don't know, but it just looks like it's just the right time to think about it.
Yeah, and I guess an easy way for us to look at it, like you said, would just be to subtract that power demand, which was brought up by in the room, because I mean a lot of the system sizing is sized for takeoff, which is why we have that post combustor, which like to the point you brought up. So if we could kind of get rid of that high demand portion of the flight, that would make the design life easier, or the simulation on the aircraft. I have a question.
That might just show up in the amount of fuel that you have to carry, because the aircraft is going to have to be redundant where it can take off on its own power without a launcher in an emergency. It can. You wouldn't want it to be dependent on the carrier.
Yeah, that's another good point. So, and this is not aircraft design work. A lot of like going into how many certifications an aircraft would need, like this is definitely too much for one small team of researchers to handle. But thinking of these kind of things is definitely the step in the right direction for, getting one of these to work eventually. I appreciate the question. Thank you.
Sure.
Any other questions? If not, if you don't have them right now, there's our contact information on the slide, as well as 2 QR codes. If you want to scan those with your phone or take a picture of them, you can get to our website, which is how you find these seminars, as well as you can see some of the work we're doing in the lab. Thank you guys again for participating and asking questions and listening to me. Appreciate it.
Oh,
Yeah, thank
just
you,
before
everyone.
just before jumping off, the one thing, and this is addressed to my first question that was in the chat, Trevor, is just trying to make clear when you talk about kilowatt hours and kilowatt, because there are kind of 2 different requirements there, whether or not you have to have that. You talk about batteries, whether or not you can discharge quickly enough and have a sustained, stable discharge over that time, or if it's kilowatt hours where you're talking about, okay, well, this is my energy storage, and so this is the amount. So certainly there's an interplay between the 2, but just in the presentation, I think it was a little bit unclear to me. The discussion was jumping back and forth between the 2. So there are 2 different issues that are discussed.
Yeah, no, that's a good point. They are different, but so you would probably need. I mean, you would need to size it based on how fast you can discharge,
Right.
because that's how you need to make up for the energy difference that you're not generating with the SOFC. So I think that would be the driving factor, because I think that is the limiting factor in most batteries is how fast you can discharge them.
Right.
So I apologize if I confused that, or mentioning kilowatt hours, but kilowatt hours is energy, and kilowatts is power, so they are very different.
Right. Because that's the thing that comes in a lot is when people talk about batteries, is, okay, well, I can get this kilowatt out of it, and then it becomes an issue, because like, well, we need to cycle this. It has to have maybe 100,000 cycle life for it. And it's like, well, if you're discharging at that rate, you're not going to get that much cycle life out of it. So just and I think those are just things to consider. If you say, okay, well, I'll just get a battery and just spec it out, and says like, yeah, the battery can give you that power, but maybe not in the subtext. It'll give you that power maybe with 5 or 10 discharge cycles.
Yeah.
Okay.
Yeah. So I mean, I think to make this work, we need advancements in both fuel cells as well as batteries. And
Sure, of course.
Well, thank you, everyone. Feel free to reach out to Trevor or myself if any other questions come up. There will be a recording of this put on the website, and you may see that there's recordings of the previous presentations, the previous seminars that were provided are at the website. And our next one is scheduled for February 14th. That will dive into some of the swap and kind of from the size weight optimization, looking from the structural side of how we get up to above 3 kilowatts per kilogram potential for this type of system. And so again, thank you everyone for attending this. This was great opportunities for the students to get out there and network and show the great work they're doing here. So have a great day. Thank you.
yep, thank you.